Imagine a metal so extraordinary that it can survive inside a jet engine at 1,500 degrees Celsius. Yet it's light enough that you barely feel it on your wrist as a watch. A metal that your body actually welcomes rather than rejects. A metal so strong it can take a bullet, but so challenging to produce that for decades, only superpowers could afford to make it. This is titanium. And here's the crazy part, we almost didn't figure out how to use it at all. Today, we're diving into titanium, a metal that took 150 years from discovery to mass production and changed everything from how we fly to how we heal. But here's the question nobody asks. If titanium is the 9th most abundant element in Earth's crust, more common than copper or zinc, why is it so expensive? Why did it take so long to figure out? The answer will surprise you. Picture this, it's 1791. An amateur geologist named William Greger discovered a new element in England. He calls it menaconite. For years later, a German chemist rediscovers it and names it titanium, after the titans of Greek mythology. But here's the twist. For the next 119 years, titanium was essentially useless. Scientists could identify it, but they couldn't purify it. Every time they tried to melt it, something bizarre happened. Titanium has an insatiable appetite for oxygen, nitrogen, carbon, pretty much anything in the air. Heated in a normal furnace, it gorges itself on these elements and becomes brittle and useless. It's like trying to diet in a chocolate factory. This made titanium the ultimate tease, everywhere in nature but impossible to use. Engineers dreamed of what they could build with it. If only they could figure out how. Fast forward to 1932. A Luxembourgish metallurgist named William Kroll is obsessed. He's trying to crack the titanium code in his laboratory, and he has a radical idea. What if we don't fight titanium's reactivity? What if we use it? After years of failures, Kroll developed a process so clever it's still used today, 90 years later. Here's the genius of it. Step 1. The chlorine dance. First, you take your titanium, or usually ilmenite or rutile, minerals found in beach sands from Australia to South Africa. You don't try to melt it. Instead, you introduce it to chlorine gas at 1,000 degrees Celsius. Think of chlorine as a better dance partner. Titanium prefers bonding with chlorine over oxygen. So you mix the ore with chlorine and carbon, and boom, you get titanium tetrachloride, a clear, smoking liquid that looks like something from a mad scientist's lab. Here's where it gets interesting. This liquid boils at just 136 degrees Celsius. That means you can purify it through distillation, just like whiskey. All the iron, all the impurities, they're left behind. Step 2. The magnesium trick. Now comes the magic. You take this ultra-pure titanium tetrachloride and lock it in a sealed reactor, no air allowed. Then you add molten magnesium. Magnesium is more desperate for chlorine than titanium is. So it literally rips the chlorine away, sacrificing itself to free the titanium. What's left is pure titanium, but in the weirdest form. When you open the reactor, you don't find a shiny metal block. You find something that looks like a gray, crusty sponge, porous, brittle, nothing like the titanium we know. This is a titanium sponge, and it's one of the most valuable industrial materials on Earth. But we're not done yet. Not even close. Step 3. The melting challenge. Remember titanium's addiction to oxygen? It's still a problem. You can't just throw a titanium sponge in a regular furnace. It'll contaminate instantly. So engineers invented vacuum arc remelting. Picture this. You take giant titanium sponge electrodes and strike an electric arc between them in a vacuum chamber. The arc is so hot, over 3,000 degrees Celsius, that it melts the titanium into puddles, which drip down into a water-cooled copper mold. No air, no contamination, just pure, gleaming titanium forming into a massive ingot that can weigh several tons. Some applications use electron beam melting instead, literally using concentrated beams of electrons to melt the titanium. It's like using tiny lightning bolts as a forge. Now we have our titanium ingot, a massive block of metal, but it's still not ready for your smartphone or that F-35 fighter jet. These ingots are reheated and run through industrial presses that exert thousands of tons of force. They're forged, rolled, and extruded into sheets, rods, and tubes. And here's the kicker. Titanium is incredibly difficult to work with. It's so hard that it wears out cutting tools faster than almost any other metal. It generates heat so efficiently during machining that it can catch fire from friction. Machinists need special tools, special lubricants, and a lot of patience. But pure titanium, that's just the beginning. The real magic happens when you add other elements. Add 6% aluminum and 4% vanadium? You get T6Al4V, the workhorse of aerospace, making up half of all titanium used. It's in every commercial jet engine. Add a little niobium? Perfect for superconducting magnets. Keep it pure? That's ideal for medical implants because it's hypoallergenic. These alloys are mixed during the melting stage, creating materials with properties that pure titanium could never achieve. It's like upgrading from a standard bicycle to one custom built for your exact needs. For medical implants, titanium is polished to a mirror finish and sometimes treated with plasma to create a surface texture that encourages bone growth. Your body literally bonds with it. For aerospace parts, they might receive heat treatment to boost strength or anodizing to create those beautiful blue, purple, and gold colors you see on custom parts. Why is it so expensive? Here's what blows people's minds. Titanium is more abundant than copper in Earth's crust. So why does a titanium bike frame cost 10 times more than an aluminum one? The answer: energy and complexity. The Kroll process requires chlorine gas, dangerous and expensive; magnesium metal, which also needs to be produced; vacuum furnaces, massive energy hogs; multiple remelting steps; highly skilled workers. Every ton of titanium sponge requires about 4 tons of magnesium. And all that magnesium becomes magnesium chloride waste that needs processing. Mining and processing titanium consume enormous amounts of energy. But here's the counterpoint: titanium parts last decades. That airplane turbine blade? It might serve for 30 years. That hip replacement? It could outlast the patient. And titanium is almost endlessly recyclable. Those aerospace scraps get remelted and reused. Nothing goes to waste. Scientists are racing to develop better production methods. The most promising is the FFC Cambridge process, named after researchers Frey, Farthing, and Shun. Instead of chlorine and magnesium, it uses electrolysis to extract titanium directly from ore. If perfected, this could cut energy use by 30 to 40%, eliminate hazardous chlorine gas, slash production costs, make titanium as affordable as stainless steel. Imagine a world where titanium is cheap enough for everyday products. Your car body, your laptop case, your kitchen sink, all titanium. It sounds like science fiction, but then again, so did flying until we figured out titanium. Titanium's story is really humanity's story, a material that existed all around us but remained locked away for over a century. Then, through persistence, creativity, and a little bit of mad scientist thinking, we cracked the code. Today, titanium is in the International Space Station, in your body as medical implants, in the phone in your pocket, and in the engines of jets flying overhead. Not bad for a metal that was useless for 119 years. So the next time you see that silvery gray gleam, remember, you're looking at something that took the collective ingenuity of generations to create. From beach sand to spacecraft, titanium truly is a metal for the ages. What should we explore next? Drop your suggestions in the comments. If you enjoyed this journey through chemistry, engineering, and human determination, hit that like button and subscribe. Until next time, stay curious.